Hello, everybody, and welcome back. We are now in Chapter 25, Meta-Analysis. We're going to discuss what meta-analysis is, the pros, and the cons. Okay. As always, you should read through the chapter first, make notations just like you would for an in-class lecture, and then we'll discuss this section just like we would have before the pandemic occurred. So, let's begin. We're going to go through just a few of the thought questions at the beginning of the chapter. Our first, suppose 10 similar studies, all conducted on the same population, or same kind of population, were conducted to determine the relative risk of a heart attack for those who did and did not take aspirin. To get an overall picture of the relative risk, does it make sense to combine these studies or to leave them separate? Well, normally this is where I would ask everybody to raise their hands who would combine, who would leave them separate. Now, there was a key word here. The key word here is same kind. All of the data all of the samples are being taken from the same general population. If I can take all of the samples from the same general population, by combining the studies, essentially what I'm doing is making the sample size larger and larger. If I'm able to make the sample size larger, I'm able to get better results. So because I'm taking the sample from the same population for each of the studies, and because the studies are similar, I should combine these values. Thought question 2. Suppose two studies compared surgery versus relaxation for sufferers of chronic back pain. One of the studies was done at a specialty back clinic, and the other at a local medical center. Result was relative risk of further back problems following surgery versus relaxation. Now, does it make sense to combine these values? Now, everybody in the study has some type of back pain. But do you think that all of these are from the same population? Do you think somebody who goes to a local clinic may have as severe of an issue as somebody who has to go to a specialty back center? Because the groups are potentially not the same, they're dissimilar from each other, it doesn't make sense to combine this study. One person may have pulled their back doing yard work, and the other person may have multiple spinal fractures. It doesn't make sense in this case to combine these values. Where in the other, because they were all similar studies and they were taken from the same kind of population, it did make sense to combine. Okay. So, referring to these thought questions 1 and 2, not 2 and 3. If 2 or more studies have been done to measure the same relative risk, give one reason why it would be beneficial to combine, and one reason why it may be beneficial to look at them separately. Well, what did we say? If I can combine, if they're taken from the same general population, and if the studies are similar to each other by combining them, I'm left with a larger sample size. And with that larger sample size, I'm more likely to have a statistically significant result. Now, what's a con of combining? Well, the one that flashes out in front of us, something we discussed multiple times in the past, Simpson's paradox. We know that the combined results may show a different pattern than the results independently. One example that we discussed with Simpson's paradox, recall, was the admissions into a particular college. What we showed was that in this particular example that we went through in our lecture, when grouped together, men at the college had a higher acceptance rate. But if you looked at the individual programs, women had a higher rate in each program. So if I combine the results, I could result in Simpson's paradox. Okay. So, on to the actual new information. The need for meta-analysis. It says most relationships we now study are moderate in size. Researchers often fail to find statistically significant results. The number of participants in a study is a crucial factor in determining whether the results will be significant. And many of the studies conducted are simply just too small to do so. And what did we say? If I was able to combine multiple studies, making the sample size larger and larger, I could potentially get to that statistically significant result. Now, it says reports often published that appear to conflict with earlier results, confusing the public and researchers. You see this a lot reading through studies, reading through the news articles. Whether you see a report going in one direction and then potentially even the next day you see it saying the exact opposite. So, but with meta-analysis, if we're able to combine multiple results or combine multiple studies, we can look at the result of those combined studies. Okay. Vote counting method is the most flawed of the techniques. In vote counting, it says to find all studies conducted on a topic and simply count how many of them were statistically significant and how many were not. It says it often discounts entirely all studies that had not and attempted to explain any remaining differences in the study by subjective assessments. So if I have 15 studies and 10 of them were statistically significant, I'm pretty much just ignoring the other 5. It says this vote counting method is seriously flawed unless the number of participants in each study is taken into account. Let's look at that example. If 10 studies of effect of aspirin on heart attacks had been conducted on 2,200 men rather than one study on 22,000, none of them would have been statistically significant. We wouldn't have a large enough sample size to have a statistically significant result with just 2,200. But by combining all of these 10 studies to have a sample size of 22,000, we would be able to show a statistically significant result. If I was using the vote counting method, all 10 of those independent studies would have been not statistically significant. By combining them, it would have shown that. So what is meta-analysis? Meta-analysis is a collection of statistical techniques for combining studies. These techniques often focus on the magnitude of the effect of each study, rather than just, was it statistically significant or was it not, rather than the vote counting technique. Okay? This is relatively new, only really beginning in 1976. So what is the purpose of meta-analysis? What can it tell us? Well, it can find definitive answers to questions with small or moderate relationships by taking into account multiple studies. So, when I'm trying to perform a meta-analysis, one of the most important questions that we ask are, what studies should be included? And am I supposed to compare the studies individually, or is it better to combine the studies? So let's see, what studies should be included? One of the questions that we want to ask is, do we want to include all studies or only published reviewed or peer-reviewed journal article studies? Now, this depends on the topic, right? This is a situation-by-situation question. How much information is out there? How many studies have been conducted? The timing of the study. Has technology changed? Has everyday life changed significantly from where we're at now to when that study was taken? if our everyday life has changed, the studies may not be comparable. It may not be something that we wanted to combine. If we were to do a study on the number of people taking online classes, looking at now versus looking at 2 years ago, those are not comparable. Okay. Quality control requires studies to meet a stringent quality criteria. What makes a good study? This was chapter 1, right? A control group, randomization, and so on. If some of the studies don't have the control group and others do, we may not want to consider anything without a control group. Okay. Accounting for the differences in quality. If we still want to include some that may not meet all of our stringent criterion, we may want to include them but not weight them the same. Just like one homework assignment doesn't count as much as your final exam, but they both count towards your overall grade, we may want to weight these studies differently based on the quality of the study. Now, how do I determine the quality? Typically, you want at least 2 people to go through, and the best method is really just a checklist. Does this meet A, B, C, D, and so on? And if it meets my criterion, that doesn't necessarily meets others. So having this done by at least 2 people independently, so you know what studies to include. And of course, you want this to be blinded. If I said a study from such and such research center, you may already have a feeling about that research center, positive or negative, where you want to include them or exclude them. So to blind these is the best idea. Okay. Do I want to combine or compare the studies? In order to combine the studies, the samples should be taken from the same population, and the studies should be very similar to each other. If I want to simply compare the two, this would be like our second thought question, comparing the results, say, of a specialty back center versus a local medical clinic. Some situations don't call for the data to be combined, rather compared. Okay. Do I have the same population? Fixed effects. Fixed effects is the assumption that all studies include samples from similar populations, and the goal is simply to estimate the effect. Let's go all the way back to thought question 1. In thought question 1, all 10 of these studies were from the same general population, and they were all similar to each other, and we're trying to measure the effect of taking aspirin versus not taking aspirin and how that affects your relative risk of a heart attack. Random effects is the assumption that the population effect is different in each study, and the goal is to estimate the variability from study to study. Here we're comparing, not combining. Again, this would be our specialty back clinic versus our local medical center. It's still going to be informative to compare the two, but we're not able to combine them. Let's look at our first case study in the chapter. Again, you should have read through the chapter. You should have already read the case study. It says 20 studies were that examined whether men who smoked cigarettes had lower sperm density than those who did not smoke. But the studies differed. 10 reported persons measuring sperm density was blind to the smoking status. 6 only defined a smoker as somebody who smokes at least 10 cigarettes a day. So if somebody smokes 9 cigarettes a day, they're considered a non-smoker in 6 of these studies. 13 of the studies used infertility clinics as the source of their participants, and 7 did not. So it says the authors conducted an analysis of all the data as well as separate analysis of 2 types of populations: those who were at the infertility clinics and those who were not. It didn't necessarily make sense to combine the two because one group already had the infertility issue and one group wasn't at that clinic. So let's see, it says, results. Using all data combined, giving more weight to studies with larger samples, again, we can assess the quality, and if we have a larger sample, we consider that a higher quality. We weighted that differently. The reduction in sperm density for smokers compared with non-smokers was 12.6%. We have a 95% confidence interval that ranges from 8 to 17.1%. So it says, test of null hypothesis that the reduction in sperm density for smokers in a population is actually 0 is less than 1/10,000th. So we clearly, for any conceivable alpha value, we would have rejected this null hypothesis. There's clearly a difference in the sperm density of smokers versus non-smokers. It says, estimate of reduction in sperm density for normal not infertile men was even higher. So when we combine the two, again, people at the infertility clinics and people who were not, we had a confidence interval ranging between 8 and just over 17%. But at the groups that weren't at the infertility clinic, they saw an even larger increase. So, it says the results of the meta-analysis indicate that smoker sperm density on average 13% when the studies were weighted and 17% when they were given of equal weight, lower than that of non-smokers. So again, the reason the studies were weighted was based on the quality, based on the size of the study. The reason for the inconsistencies in published findings with regard to the association is typically because of very small sample sizes and, of course, random error. So consequently, the power is low and there's a high chance of a false negative. And remember what the power of the test is. The power of a hypothesis test is the probability that the test correctly rejects the null hypothesis. By being able to combine these values, combine the studies that had small sample sizes, I now had a larger study with a large sample size, and I could actually get statistically significant results. Now, be careful what kind of study this is. Did I take a group of men and say, this half of the group has to start smoking, this half of the group's not smoking, and then measure the sperm density after? No, this is not a randomized experiment. And because of that, we still have the potential of confounding variables. One obvious confounding variable that jumps out to me is stress. Stress could be related to both smoking and the sperm density. Some benefits of meta-analysis. Detecting small or moderate relationships. Obtaining a more precise estimate. A nice, interesting one is determining future research. And then, of course, finding patterns across multiple studies when we're comparing studies. Okay. So let's talk a little bit more about each. Again, if I have a very small sample size, it's going to be difficult to detect a relationship. But if I increase the sample size larger and larger by combining studies when I'm able to combine them, I may be able to actually see this small or moderate relationship. Similarly, if I'm able to combine studies, I would get a more precise estimate of the relationship. We saw what happened with my confidence intervals. If I increased the sample size, the width of the confidence interval decreased. So I'm able to obtain a more precise estimate. Determining future research. Based on the meta-analysis, it may show something that we weren't able to see by an independent, smaller research or independent, smaller study. And that will put us now in a new direction. What should we study now? And of course, on its face, this one's obvious, finding patterns across the studies, being able to compare the different studies and seeing the patterns. All right, so let's look at our example. Designing better experiments. Early meta-analysis to study extrasensory perception, or ESP, had many flaws. We discussed this ESP example previously. Remember, ESP, the idea that I can perceive in my mind what's happening, even if I can't see it. One of the studies that we discussed was the idea of somebody holding up a photograph and it's facing the opposite way, and you're supposed to tell them what's on the photograph. All right. So, the problem with this early meta-analysis is that it had improper randomization of target pictures or sloppy data recording. It says early studies of photographs that senders were supposed to transmit mentally to the receiver. If the sender was holding that picture, think about when you pick up a picture or a piece of paper. You might have fingerprints on the picture, you might have crinkled the picture, right? Smudge mark something. You're supposed to be able to determine using ESP which picture this was. Well, that's not, you don't necessarily need ESP to show that one of the pictures has a thumbprint and the other doesn't. So now using newer studies, it says the new experiment in case study 22.1 was designed free of these flaws. And this was our first meta-analysis. Let's look at another. Grouping studies by orientation. It says this compared adolescent smoking prevention programs characterized by having one of four orientations. Rational orientation. Lectures and displays on the substances. This is what smoking is. This is what a lung who smokes looks like. This is what a lung of a non-smoker looks like. Developmental orientation. Lectures, problem solving, role playing. Social norms. Participation in community and recreational activities. And social reinforcement. Role-playing, and a public commitment not to smoke. When I was growing up, this social reinforcement was what we called the DARE program. Why do I have this highlighted in red? Well, when we actually compared the studies using meta-analysis, we saw that the rational had very little, if any, impact on whether an adolescent would smoke. The developmental and social norms were similar in impact, but by far the most effective was social reinforcement. So by comparing, people were actually able to determine what is going to be the best program to keep adolescents from smoking. All right. Criticisms of meta-analysis. As we previously stated, if I choose to combine the data, I could result in Simpson's paradox. Right? Having different results separately than I do combined. Confounding variables. Having differences between the studies. Subtle differences in the treatments that are given the same name. We're going to go through an interesting example with that. The file drawer problem, which I like the name, and we'll explain why. Biased or flawed original studies. Practical versus statistical significance. and finding no difference. Let's jump in. Okay. It says meta-analysis is essentially observational. So various treatments cannot be randomly assigned across the studies. There may be differences across the studies that aren't clear. And again, the next one being subtle differences in the treatments with the same name. If I'm comparing the effect of chemotherapy, if I said patients were given chemotherapy, there's a difference between giving chemotherapy once a week or twice a week. If I just generically called it chemotherapy, I may have combined them when I shouldn't have. The file drawer problem. Some studies may not be discovered by meta-analysis. It says it's likely studies that did not achieve statistical significance and thus were never published. If I went through years of research and my results were not statistically significant, it's unlikely that I'm going to rush out to try to publish those results. Hence, they're still in my file drawer. So when I'm trying to combine studies, that may not be published, which means it may not be something I can find. I may not be able to combine those studies. So one workaround is if you're researching and trying to combine meta-analysis, look at the people who are actually researching the topics and actually ask if there's any unpublished information that you can combine. Biased or flawed original studies? Of course, if the original study is biased, then the meta-analysis will also be. Practical versus statistical significance. It says meta-analysis is likely to find statistically significant results because we're going to have a substantially large sample size. It's important to learn the magnitude of the effect of the meta-analysis, not just whether it's statistically significant. I may be able to show that there are people, or that people driving down 322 on Rowan's campus, that instead of driving the speed limit of 25 miles an hour, they're driving 25.1 miles an hour. With a large enough sample size, I may be able to prove that they're driving faster than 25, and it may just be 25.1. But is there a practical significance between 25 and 25.1 miles an hour? You could publish the study and say, we have a statistically significant result that people were driving faster than 25 miles an hour, but is 25.1 really making a difference? And false findings of no difference. Meta-analysis can erroneously reach the conclusion of no difference. And that's simply when we don't have enough data to find a statistically significant result. So just because something's not statistically significant doesn't mean that there's actually not a difference between the two. It's just not something we were able to prove. Mammograms. Our second case study. In February 1993, the National Cancer Institute convened an international conference. Meta-analysis conducted on the effectiveness of mammography as a screening device. Results for women 40 to 49 years was, for this age group, it is clear in the first 5 to 7 years after study entry, there is no reduction in mortality from breast cancer attributed to the screenings. What they're claiming is that there's no benefit of being screened, of having a mammogram in this age group after 5 to 7 years of the study. The research actually led to the withdrawal from the National Cancer Institute of supporting mammograms for people under 50. But of course, the National Cancer Society refuted the study and announced that it would not change its recommendation. The meta-analysis considered 8 experiments conducted over 30 years, 500,000 women. 500,000 women is a very large sample size. But not all the studies even included women under 50. So even pulling the data of all 8 randomized controlled trials produces insufficient statistical power to indicate the presence or absence of a benefit of screening. In all 8 trials, there were only 167,000 women, about 30% of the participants, and the number was too small to provide a statistically significant result. If the numbers were too small to provide a statistically significant result, then the results were what? Inconclusive? And while the National Cancer Institute said there's no reason for the mammograms, the National Cancer Society said that they should keep them. Okay. So, this was chapter 25. We have 1 chapter remaining for our entire course. I'm going to post both chapters on the same day. I'm going to post them both on Monday, April 27th. This way you have an entire week to go through the chapters, to read the chapters, to watch the video, and email me, message me on WebAssign with any and all questions. Have a nice day, everybody.